In this lecture, we will provide some training tips and tricks that may be useful when training deep learning models. We will start with a quick review, then discuss overfitting, data augmentation, and end with a discussion on training, validation, development, and testing. In classical machine learning, traditionally, you have an image that is end by end, and you engineer a smaller set of K features. These features can be, for example, the ratio of the length to the height of the object, or the number of circular objects in the image. Then you apply your favorite algorithm to learn to associate these patterns of features with an identity. In this case, vehicle. With supervised learning, machine learning algorithms use pre-labeled training data to infer a function. Here, imagine that you're trying to classify an image into 5 categories: vehicles, animals, faces, fruits, and chairs, using 2 features, the 2 axes here. Supervised learning, using the machine learning algorithms listed here, allows for the determination of decision boundaries, shown here, using pre-labeled data. Here we can see that while the decision boundaries are not perfect, they do a reasonable good job classifying the data. We'll now talk about overfitting, a common problem in machine learning. These decision boundaries, when looked at the training error, perform with near perfection. However, when we apply a new data set, we can see that the decision boundaries have memorized the training data set and actually perform quite poorly when testing, as compared to the previous decision boundaries. This problem is called overfitting and is common in machine learning. The graph on the left shows what underfitting would look like when the machine learning algorithm cannot capture the underlying trends of the data. In this case, the testing error and training error would be both high. The middle graph shows a well-trained model. The testing and validation error is at a minimum, and the training error is relatively low. On the other hand, the graph on the right shows overfitting, where the training error may be lower, but the test error is higher. Overfitting can be an issue with larger networks, as they have lots of weights. These networks can memorize the weights that perform excellent on the training dataset, but does not generalize and has poor predictive performance. Suppose that we have this dataset, and say that we have 2 models which have been trained on this dataset. We can see that the first model performs with 100% accuracy, while the second does not, but it's still close. When estimating the value of the point shown in red, we can see that the model on the far right is much closer to the ground truth, despite having lower training accuracy. Let's look at another training trick, data augmentation. Data augmentation is often used when the training data is not sufficient to learn a generalizable model. This can be done by slightly altering the original image, whether that may be by mirroring it, cropping it, or stretching it. There are dangers with simulated data, as the data is not exactly what you would find if the data was collected. But if done correctly, data augmentation can be a powerful tool. One must be careful to only augment in realistic ways. For example, flipping a cat upside down would not be a good way to augment the data, as you would probably never expect to find an upside down cat in real life. We'll end this lecture by reviewing tips for minimizing training and testing error, among others. In order to reduce high training error and high validation error, you may use these techniques. For high training error, bigger models and longer training will help. For high validation error, more data, more regularization such as dropout and weight decay, and early stopping are effective techniques. Finally, it is generally best to use a large model to overfit the data, and then fix the overfitting afterwards. Additionally, the validation and test data should be from the same distribution, and it can be easier to break a task into various pieces. For example, Baidu uses 4 different networks to convert text to speech, and autonomous driving models use numerous networks. In this lecture, we have explored methods to prevent overfitting, data augmentation, and other training tips and tricks that may be useful when training deep learning models. During the next lecture, we will discuss multi-node training in order to minimize the time to train.
In this exercise, you will examine the concept of overfitting, where a model fails to generalize its performance to unseen data, such as a separate validation set. You will also learn how to recognize overfitting using visualization tools, and how to apply dropout to prevent overfitting. Here you will use a simple convolutional network on the CFAR10 dataset. After running the model, you should notice that in the logs of the model, after around epoch 15, the model begins to overfit. Even though the cost on the training set continues to decrease, the validation loss flattens and even increases slightly. You can visualize these effects using the code provided. In order to correct this overfitting, you will introduce dropout layers into your model, which randomly silences a subset of units for each mini-batch, which greatly helps overfitting. Add these to your model as indicated in the exercise and compare the generated plot with the plots associated with the model without dropout. You should notice that the validation loss in blue is not shifted downwards compared to the previous figure, and the model reaches a better validation performance.